So yes, we started the recording for today's class, which is class 9, class number 3. One of the things that I would like to show you okay, I picked up this image to explain something important for all of you. One of the things that I would like you to kids to appreciate that whenever we have a perfect geometric figure, for example, a straight line, if we're trying to find out the area under a straight line, ideally it's quite simple and easy to achieve. For example, if we have a x-axis and y-axis like this, let's say for the sake of discussion, in some case this is speed axis and this is time axis, so v versus t graph, pt graph. If you have a straight line for this scenario, you can very easily calculate the distance covered of this object for any duration of time. If you don't have straight lines like this, in many cases you can have segments of straight lines like these and these, and then let's say like these. So if you have the values which are all, if this entire graph is plotted on a graph paper, you have the grid lines and everything, you can also calculate areas of multiple segments as you require, which is pretty easy. We can go for the triangle rule, rectangle rule, or we can go for the trapezium rule, which also works. One of the things that we do come across a problem is that whenever we have to try to calculate the area under a curve, so a curve that might as well look like this. Important bit is that we cannot essentially calculate the curve by calculate the exact area of a curve by using a geometric method. The recommended way to the recommended or the reliable way to calculate the exact area under a curve is to go for integration. Integration is something that I don't think you kids have come across yet. Have you? In your maths, did you come across integration yet?
No, sir, we haven't.
No, sir.
You're not supposed to. So for our physics syllabus, for most part, even all the way up to our A2 level, you wouldn't be doing integration for your physics syllabus. Although you kids will be introduced to the idea of integration in your O levels, and for those who will pick up math in your A levels as well, you will essentially have to go through a rigorous amount of integration maths, which is pretty fun at some points, provided that you can make sense out of it. But for your physics syllabus, the integration is not made to be a compulsory thing in your physics syllabus, in the Cambridge syllabus. So in most cases, we have to go for the calculation of area under curves by some sort of estimation. Now, what kind of estimation am I talking about? Let me talk about this curve over here. Have a look. Let's say this is a graph that we have available to us, and we want to calculate the area of the graph from 1 to 4. So to make this happen, this is a smooth curve. So we cannot essentially consider this entire curve to be a straight line. So assuming a single trapezium under this whole thing, for example, assuming a single trapezium, let me draw with green, assuming a trapezium of this much would be inappropriate. If we have to assume this whole thing as a single trapezium, you can see it very well that this side of the trapezium, I mean the top side of the trapezium, is not essentially a straight line. It is visibly a curve. So one of the ways we can solve this problem is by doing some generalization, or something that we call simplification. The simplification is, as you can see in this figure, that the process is that we have divided this curve segment into multiple small parts. Now, whenever we are dividing this thing into small parts, effectively we are considering each of this part as a straight line. So let's say we are assuming this as a straight line, and this one as a different straight line, this one as a different straight line, this one as a different straight line. Now, if you wonder that how is that even a straight line? If it's a curve, it's a curve, period. True, it's a curve, period, true. But the idea is that whenever we consider a very small segment of a very large curve, practically we can consider that segment to be a straight line. We can consider it to be a straight line. So the method is that we can go for calculating the, you can go ahead and calculate the area under the graph using the, considering them as trapezium. For example, in this graph, they are showing only rectangles, so this might be a bit confusing for you, but don't bother. What we can do is that we can consider this part as a single trapezium, and we can go ahead and calculate the area of this one individually. Then we can take this one as a second trapezium. We can consider this one as a second trapezium. We can consider this one as a second trapezium, and so on and so forth. If you wonder that will this procedure be ever 100% correct, the answer is a solid no. But this is a process of approximation. So let me explain to you, what do I mean by approximation. Approximation means something to measure something, to not to its exact value, but to a functional acceptable margin. For example, let's say if it's asked that what is your weight, you get a number, you give us a number that this is my weight. This is the measured weight that you have measured on a weighing scale sometimes earlier, and this was the weight of your body, or this was the mass of your body. Weight is the layman's term for mass, but we should use mass. This is the mass of your body at that instant, and that is not actually your net mass, because it depends on a lot of factors. When was the last time that you had a meal? When was the last time you had a bottle of water? When was the last time you peed or pooped? And also the mass of the dresses and your cell phones and your money bag, everything that is attached to your body, everything all together add up to the mass that you have measured. So this is something that we call gross amount, or an approximated value. So your mass is something around that value. This is not your net mass. To get to your net mass, we would essentially have to we have to set up some standard. For example, let's say if I want to get my exact mass, I might as well go through a starvation period of, let's say, about six hours, and then I might have to take my weight being naked and everything, so I get the exact mass of my body molecules. But that's not essentially something that we do not go through. The idea that I'm trying to transfer here is that if we are trying to measure something, there is always some limit of acceptability, that up to how much precision can we say that this measurement is accurate. Let me give you some idea of approximation, or the idea of negligibility. When do we essentially consider some physical quantity to be negligible, and when can we actually consider some value to be significant? Let's say you are trying, should this example be a good one? Yeah, this can work. Let's say you are trying to measure your height. Now, from the idea of mass, I'm moving to the idea of height. If you're trying to measure your height, you can measure your height, and you can go ahead and you can mention that. Now, come to think of it, if you measure the height of a person, let's say that height is about 5 feet 6 inches or 5 feet 7 inches, somewhere around 1.7 meters. Would you think the thickness of the hair in their skull would actually matter to their height? For a regular person, that is. For a regular person, it should not matter unless that person has a very thick afro. Do you guys know what afro is?
No, sir.
Let me show you.
Yes, sir.
What an afro is, so that you get my point. This is what we call an afro. So these are all women. I would like to have male people. Yeah, have a look at this one. Maybe Bob, this guy looks like Bob Ross. So if you're trying to use, this is amazing, hilarious. Anyway, so if you try to measure the height of this person using some touching mechanism that will hit the top of their head, or even for this person, for example, I mean, you can see it very well that this is a very dense hair, and you are not going to reach to the exact scalp of this person if you are trying to push something from the top and measure the height from the heel all the way to the top of the hair. So in this case, the hair can give you some wrong reading, but that's a very specific case. But if you consider for a regular person like me or you, or regular people who belong to our country, the thickness of all the hair is not actually a very important thing. So if you go bald on a day of your height measurement, you might as well say that's a correct measurement. If you have a whole head full of hair, that might also be considered as a correct measurement, because the entire thickness of hair is too much small of a fraction compared to the entire height of a human body. So what I'm talking about, the term that I want you to highlight or to take your attention to is the word fraction. too small of a fraction. The entire thickness of hair on top of our scalp is too small compared to the entire height of our body. So the thickness of the hair might not matter for a regular person's height. But if I ask you that does it mean that all the thickness of the hair of that a person have is 0? Would that mean that? In terms of measurement, it is never 0, because you can have precision measurements, vernier caliper, screw gauges, or electron microscope. Lots of precise measurements mechanisms are there. We can essentially measure how much is the total thickness of that hair. We can do that. So minutely speaking, the value of the thickness of the hair is not 0. But whenever we are trying to express the human height, for that measurement, the height of the thickness of all the hair can be considered to be negligible. So I need you to understand the whole idea between 0 and negligible. Negligible is an aspect that you can apply to a certain scenario when you are trying to diminish the effect of a very small thing compared to a very large thing. For example, let me give you another example. Let's say if I'm making a walk, regular walk, not fast walk, regular walk through atmosphere, I mean, you will experience air resistance. That is a given, because you are going to move through air particles. As you move forward through air particles, you have to push out the air molecules out of your path so that you can essentially make your way through the air particles. And by Newton's third law, as you will push on the air particles to make your path, before the air particles move out, they will also exert equal and opposite force onto your body. So as you move through the atmosphere, you will be also experiencing air resistance. But whenever a person is moving pretty slowly, let's say they are taking a walk at let's say 5 kilometers per hour or something like that, 2 kilometers per hour, covering 2 kilometers distance in 1 hour is actually pretty large. Yes, let's say 2 kilometers per hour. We can effectively say that the air resistance is negligible, because that value would still be non-zero, but compared to the amount of force that the person will be using to move themselves forward, compared to that force, the amount of force that the air resistance will exert for that low velocity will be essentially small, too small to take into account. This might add to the force, this might change the resultant force in the fifth, fourth, fifth, sixth decimal place or something like that. So we can consider that air resistance to be negligible. But if the question is asked, is the air resistance 0? That answer is a solid no. Air resistance is not 0, because he's moving through atmosphere, he's continuously colliding with the atmospheric particles, so there is air resistance, but that is essentially considered to be negligible for that scenario. But that would not be the case if you're in a car that is going through atmosphere at 100 kilometers per hour. In that case, you cannot take air resistance to be negligible unless it is a defined scenario for your defined logic for your question. Now, what do I mean by defined logic? সেটা একটু পরে আসতেছি. So this is the idea that I want you to understand between something that is to be defined to be 0 and something that is defined to be negligible. There is a pretty large gap between these two factors. I would like to complete my example of the idea of negligible about the height thing. The example that I was going by is that whenever we measure the person's height, the thickness of the hair is considered to be negligible. Now, let's say another example. Let's say you are standing on the ground, and we are trying to measure the diameter of the Earth. So if we measure through the center on the other side of the, if we measure the length of the other side of the Earth to the center from your feet. So what I mean is that I'm going to show you a figure. That figure is definitely not going to be drawn to scale, but try and appreciate the content. Let's say this is Earth, and figure not drawn to scale. Let me show the Earth in brown. And let's say this is you. You're standing here. Let's say you being a Bangladeshi person, you're also a brown guy. Figure not drawn to scale. Now, do you understand what does this word mean? Figure not drawn to scale. Do you guys understand what this phrase mean?
It is not exactly in scale.
Accurate measurements are not taken.
Proportional measurements are not taken. I might put it that way. Figure not drawn to scale means that all the things that you are seeing on this figure, they were magnified or diminished just because we wanted to show everything. Because if I want to draw a scalable figure of Earth and human being present on the Earth, I would have to show a very large sphere for the Earth and a very small person for the person. So I might not as well be able to keep the entire earth in my screen. But and also if I have to draw the earth to scale on my screen, this person might as well look like a diminishing dot over here. So I cannot necessarily show you where this person is. So figure not drawn to scale means that all the length measurements that you can see in the figure, they're not proportional. So you have to have some secondary source of information other than your figure where the exact length measurements are available to you, are made available to you. So that is another important bit. So another thing so the point I'm trying to make, let's say if for a practical case, if we are trying to measure the diameter of the earth and that we measure from the person's feet to the center on the other side, let's say this is one measurement. Let's say this measurement is, let's say A, and then if we take another measurement from the tip of their head all the way to the other side of the earth, and let's say that measurement is B. How much difference will these two measurements be in your idea? What do you think? In a practical case,
Very less.
how much difference is that gonna be?
Almost negligible.
That exactly my point is that, I mean, come to think of it, mathematically speaking, the difference of these two lengths is essentially your height. But if I express these numbers in their exact values, this height amount might affect the value of A and B up to beyond a very, very large. For example, the radius of Earth is approximately, as far as I remember, average radius of Earth, that is 671 kilometer. So that is about 6.371 into 10 to the power 6 meter. And I, being a human being, let's say my height is about 1.6 meter. So I would be affecting this number in the 6th decimal place. Do I make sense? 1.6. So if you want to put this over here, I mean, this number added with this number might as well look like this: 6.3710016 into 10 to the power 6. So this 1.6 meter is affecting this entire number at around in the 6th and the 7th decimal place. So that's where the height of a person can be considered to be negligible whenever we're trying to measure the diameter or maybe radius of the earth. So this is actually the radius of the earth. So I actually showed you the diameter. So I might as well rub this off. I'm sorry, I don't remember the exact diameter of that. I meant to say radius over here, but I actually mistakenly showed you diameter. So forget this diameter part. Let's say we are measuring the radius because I remember those numbers. So let's say A and B are the two radius. One is without the person's height, and one is with the person's height. Point being made that in this case, the person's height altogether can be considered negligible. So that's another scenario. If you take another scenario, let's say if you take the celestial case, for example, let's say here is the sun and here is Earth. Where is Earth? So let me draw the sun a little bit bigger. Here is sun and here we have the Earth. Now, if you try to measure the distance from sun to Earth, okay, the radius of Earth is practically negligible for measuring the distance from the center of the sun all the way to the center of the Earth. Now, just to convince you of this fact, I can show you the exact numbers for what I'm trying to mean. Let me get you some numbers.
$150 million kilometers.
I need to get this center to center. Something like that. It's pretty large distance to be honest. How far is the sun from the measuring the distance? Now also scale astronomical unit. This might help us. Should it help us? Okay. So yes, distance from the sun, the Earth is 149,600,000 kilometers. This is the amount of distance from the Earth to the sun, or from the sun to the Earth. So this many kilometers, right? So if I want to convert this into meters, I'll have 3 more zeros. So if I write this in standard form, this would be 1.496 into 3, 6, 9, 11. Okay, so let me try and write this. 1.496. This distance between center to center Earth is 1.496 into 10 to the power 11 meter. That's the distance from the center of the sun to the center of the Earth. Whereas the radius of the Earth was how much? We just saw a little bit earlier. Radius of the sun was, radius of the Earth was 6.371 into 10 to the power 6. So this radius was 6.371 into 10 to the power 6 meter. So you can see over here that this number is about 10 to the power 5 times bigger compared to the radius of the sun. Which means if I want to add this number over here, this number will add up to this number in the 5th decimal place. Pretty much similar to what happened over here. So in this case also, I can consider that when you are trying to consider the distance between the sun and the Earth, we can effectively consider the radius of the sun, radius of the Earth to be a negligible value. So it's important that you understand the gist of the discussion. I'm not trying to tell you some numbers are too small, some numbers are too big. I'm not trying to brag you about numbers, because these numbers don't belong to me. There's nothing to brag. The only point that I'm trying to transfer across is that you need to understand the idea you need to understand the idea that in which cases can we consider certain numbers to be negligible. It's only that some number which is too small compared to a much bigger number that we are considering, in those cases we can practically consider some things to be negligible. So coming in through the entire discussion, if you're measuring the human height, the thickness of all the hair is negligible. If you're trying to measure the Earth's radius, the height of a person can be negligible. If you're trying to measure the distance from the sun to the Earth, the radius of the Earth can be negligible. Then again, if you go even more astronomical case, for example, if you consider the Milky Way galaxy, let's say this is the Milky Way galaxy, and here is the central black hole that we have, and sun is solar system is somewhere over here, solar system. So if you consider the distance from the solar system center to the center of the Milky Way galaxy, this distance is too big compared to this distance as well. So for this case, the entire solar system can be considered even smaller than a speck of dust in scale. So there is no such distance that can be considered to be too big. There is no such distance that can be considered to be too small. It all comes to the idea of perspective. It all comes to the idea of application, that what should we consider as a considerable number and what should we consider as an insignificant number. Could I make sense with all of these ideas, discussion? Does it make sense to you?
Yes, sir.
Any questions so far? Please respond. If you have a question, just ask it through. You can unmute yourself or you can write it in the chat window, however you're comfortable.
Sir, I didn't understand this sun. I didn't understand this fact about the galaxy.
This last one?
Yes, sir.
Oh, if you consider that this is the size of the Milky Way galaxy, okay, let me just show you a figure, so that might as well be easier for you, since we have access to internet. So why not? Yellow. I can go for search over here. Milky Way galaxy and solar system So if I go for images, and so this is sort of the top view. This is not a very high definition image though. Okay, yeah. This is a more or less high definition image. So this might as well work. Or should this work? Okay, I might as well use this information. So have a look at this figure. No, I don't want any advertisement over here. কপি ইমেজ করে এখানে পেস্ট করে দেখাই, তাহলে একটু বুঝতে ইজিয়ার হতে পারে। আমি এই গ্রাফটা নিয়ে আরেকটু আলাপ করব একটু পরে, but let me just finish up this discussion about the idea of scaling. So if you have a look at this thing, this is actually a computer generated image of the Milky Way galaxy. This I don't think any of our probes actually took this picture. I'm not sure if any of our probes did took the picture.
Sir, they haven't.
they haven't so far, because taking this entire view of Milky Way galaxy in a shape like this would be extremely
They
difficult.
haven't even crossed the solar system.
We have crossed the solar system.
No, just between the Earth clouds.
Yeah, exactly. Yeah, exactly. So this is a computer generated image from all the information that we have. So this is not an actual taken image. But what I'm trying to mean is the solar system is somewhere over here. And compared to the entire size of the Milky Way galaxy, the solar system is not even visible. Can you see sun and planets over here? You don't. You see just dust sort of stuffs. So the point that I was trying to make is that if you try to measure the distance from the center of the Milky Way galaxy to the location of the solar system, this distance is astronomically big compared to the radius of the compared to that distance from the sun to Earth. So that or the entire radius of the solar system for all I care. So if you're measuring this distance, for that distance, this one is even small. For this distance, this one is too small. So that's what I'm trying to come across. বুঝতে পারছি?
Yes, sir.
আচ্ছা, আদিন হাঁটু উঠাইছিলা, বলো, কোশ্চেন বলো।
স্যার আপনি একটু এখানে যাবেন, মানে ইয়াতে গ্রাফে আপনার এটুকটা বুঝিনি, এই যে এটুক,
এই রেক্টাঙ্গেল, আচ্ছা আচ্ছা আচ্ছা, এই পার্টটা,
জি স্যার।
আচ্ছা এই পার্টটা আলাপ করবো, সমস্যা, ডোন্ট ওয়ারি। So acha, I'm gonna get into the idea of graph calculation in detail. Don't worry about that. We are gonna actually draw a lot of graphs through questions as well. But my question finally is that, did you understand the idea of negligibility?
Yes, sir.
One more
Yes,
thing
sir.
that I did pass across, and I said I said that unless it is a predefined clause জিনিসটাকে সেটা একটু তোমাদেরকে বুঝাই। যেমন হচ্ছে আমরা যখন কাইনেমেটিক্স বা মোশন রিলেটেড ম্যাথস গুলি করব বা প্রবলেম গুলো সলভ করব, in all of those problems we're going to come across a basic definition, even all the way up to your A2 level as well. We are not going to consider a resistance in your mathematical problems. We are not going to. So the whole idea of a resistance is going to be is going to remain untouched for your A2 syllabus all the way up to in physics. Now you might wonder, that's not good, because air resistance is a physical force that we do experience. So why is that? One of the very simple thing that I would like to add to you is that whenever we learn something or whenever we try to recreate something of a physical phenomenon, it is for our own benefit of understanding and transmission of information. What we really appreciate is that we do not try to create the entire complexity of the whole situation in a single go. This is something like, let's say, this is something like, what can I say? No, I shouldn't. No, I'm not going to give an example. So we do not prefer to create all the complexity at the same time. So let me give you a simple idea. Let's say, if you want to learn about human beings, let's say I tell you that study human beings. So it wouldn't be a good idea to try and study all of the human beings at the same time, because there are so many aspects that you can study. Technically speaking, we human beings, what we actually understand, that what is a human being? We are basically our consciousness, the senses that works within us. So basically that's consciousness, or that ability to perform and conceive, that lies within our nervous system, basically the brain. So we are our brain, which that brain is encapsulated in our skeletal system, which has flesh armors and actuator mechanisms, which is covered with skin. So basically we are our brain, which works with the nervous system and which is supported by our skeletal system, that is run or covered or somehow armored by our flesh and everything. So that's one way to look at the human being. But there are more to this thing. How does the digestive system works? How does the nervous system works? There are so many different things, aspects to study. Now it is not a good idea that if you are trying to learn about human beings, that you try and gallop all of the knowledge at the same time. That would be a wrong procedure. You need to take one bite of the chunk at a time, absorb that, then move forward. That's how the basic learning process for us human beings work. So one of the ways that the scientific researchers actually work, or hypotheses or theories and ideas work, is that we primarily make a very simplified version of a very complicated thing. And then we slowly start adding up the complexity factors. Simply put, a person is moving through, a person is, let's say, moving through, is making a run on a sidewalk. So what are the factors that are involved over here? This person is exerting force onto the ground. By Newton's third law, the ground is exerting him some force in the forward direction. So there has to be significant friction force between his leg and the pavement surface, so that he does not slip off, so that he can get the necessary forward force. So friction is a helpful factor over here. Then again, as he is going forward, every part of his body is not moving at the same velocity. Come to think of it, every single time a person runs, the feet that steps on the ground, that feet remains stationary with respect to ground as long as the contact is made. Try to visualize this thing. Okay, let me just no, I want you to visualize. Use your brain. A person is making a run, so he is stepping on the ground, and then he's lifting up his other feet and moving his feet in at the duration and making another step onto the ground. As long as that other feet is moving, the first feet was actually stuck with the ground on the same location. He places the second feet onto the ground and then lifts up the first feet, and then he moves it forward. So every single instance, one of the feet is actually stationary with respect to the ground. So all of his body parts are not having the same velocity. This is also equally applicable for cars as well. If you consider for a car that is moving forward, no matter how much speed that is, if you consider at a certain instance, the part of the tire wheel, that is the part of the wheel that is in contact with the road surface, that part of the tire is basically at rest with respect to the road. Because if that part of the tire is not at rest with respect to the road, it is gonna skid. Skid means it's gonna slip off the road surface, and you cannot move forward because the car would not get the reaction force in the forward direction. So different parts have different velocities with respect to the surrounding or with respect to the road, which is a given. So this is a complex scenario. So other than going into this complex scenario first, what we can consider, let's assume that the entire person is a particle. So what do we mean by the idea of particle? In physics, the idea of particle is very simple, but it can be somewhat mind-boggling. Is that the idea of particle is something that you can, this is a thing which has a significant amount of mass, but it has zero volume. So a particle has the size of a point. We covered the idea of point in our last class. It's a geometrical being that only has existence, but it doesn't have any dimension. So a particle is basically that, but along with its existence, we are adding a second property, that is mass. So some mass that has zero volume is what we are calling a particle. Now you might wonder, that is highly impossible. I mean, for that to happen, we have to consider that the density of that object is supposed to be infinite, and because density is given by mass by volume, if you have some numerator that is a number, whereas the denominator is zero, you get an infinite value. So density might as well be an infinite number. But point to be noted that, yes?
Sir, does point has one dimension?
No, it has zero dimension.
It has zero dimension.
Length has one dimension.
And okay, sir.
The length has one dimension. If I start from the beginning, the point has a zero dimension, length has one dimension, surfaces or planes, they have two dimensions, and three-dimensional objects have three dimensions. Four-dimensional objects might have a fourth dimension, which we believe to be time. They should be moving in a fifth dimension, which might be temperature, might be something else. But we human beings have all hypothesized beyond the realm of the third dimension, because we cannot actually perceive them. So there can be a lot of mathematics that is done around this part, which works with the whole string theory and everything, but they were never proven, at least not yet.
Okay, sir.
Okay, the idea of dimension is actually pretty interesting and very amazing to explore, as long as you don't feel bored with physics. But I'm not going to get into that for your class in your class duration. But this is something that I personally like a lot. I like a lot. কি বলতেছিলাম জানো? So the idea of particle. So in physics, the idea of particle essentially mean that something that has some significant mass, but it has zero volume. Now, having zero volume would is actually not practical, but it actually helps. How does it help? If you consider an entire object as a particle that is located at the center of gravity or the center of mass of that object, you can get rid of a lot of variabilities. For example, come to think of it, let's say you have a cube. Try to visualize a physical cube. If you try to apply a force onto the cube in a direction, you'd expect the cube to move in that direction. That's a given. But as long as you consider that thing as a cube, along at the same time the cube moves forward, it is possible that the cube is going to also have some rotation. Think about it, that there is a cube at any orientation in a space, there is no gravitational force. Don't assume the cube to be located on a surface. Assume that the cube is floating in space. It's an isolated system. And you are gonna give it a push with your hand or with something else. And then the cube is supposed to move forward. But the question that I'm asking, will the cube move forward only by moving forward? Or is it also naturally gonna produce some rotation? What do you think?
Gravity, because of
Some
gravity.
rotation.
No, I'm not talking about gravity. Assume that the cube is in the space, is floating in the space. Or in other example that I can give you is that in football, I mean there are different type of carved shots, right? Like you can take banana kicks and everything. For those of you who watch some football, do you know what I'm talking about?
Yes.
Like
Yes,
the
sir.
carved kicks. Okay, so the way these carved kicks are made is that you set a certain spin on the ball as you make the hit forward. Someone is adding noise to the channel. Please mute yourself. If you're not asking a question, please take care of that problem from your side. I really appreciate that. So when the ball is made to spin, it can give you a curve. Now this spin would add a second variable to its motion parameter. But if you consider that football to be a particle which does not have any dimension, the only way you can apply a force is if you exert the force exactly at a single coordinate. You apply the force anywhere else where the particle is not present, you cannot apply force on the particle. So the only logical way you can apply the force onto the particle is only at this direction, and that force will only make the particle to move. The question of rotation is not going to be involved, because simply put, the particle doesn't have any dimension. So how could you possibly rotate that? Do you get my point? A sphere, a cube can
Yes, sir.
have a bit of a rotation whenever you exert a force onto this thing, provided the force is not directly along the center of gravity. But if the force is a bit offset, then there is always a possibility, which is the most common scenario, that the object along with its forward movement will also give us some rotation. Now if you want to measure all the factors all together, you have to calculate the rotation as well. We can completely get rid of the idea of rotation if we assume that object to be a particle. Now, this is the idea of simplification. What I'm trying to get in your head is that for the sake of easier perception, for the sake of easier understanding, we can consider an object to be a particle. But this is not practical, but this is helpful. So you first get the motion parameters done, then you can slowly start adding up all the other complexities. Then let's say now you can start to consider the object to have a linear dimension. So let's consider the object is not essentially a particle. Let's consider the object to be a line. So if you consider it to be a line, it can have rotation like a linear object, or you can have roll or spin. Then you can consider the object to be a plane. Then you can consider the object to be a three-dimensional object. So slowly, if you slowly add up one factor at a time, solving the problem or understanding the problem becomes much too easier. This is very much like building up a building, that you do not pop the building out of thin air at the same time. You make the basement, then you make the first floor, second floor, third floor, you slowly go up forward. So something like that.
So
And then,
spherical objects.
yes?
So spherical objects basically rotate, whereas linear objects tend to spin or roll.
That's what I believe. I mean, rolling is essentially, I mean, if you consider an object to be linear, or if you consider an object to be not a particle, but rather a straight line, we might as well consider that object would not, I mean, we can observe that line object's motion as it rotates about its axis. So there will be only one center, which is the midpoint of that line, and the object can rotate about that axis. Rolling would still not be observed unless you convert that thing into a cylinder. I mean, you can essentially see the rolling action if you go to the third dimension and make this straight line into a cylinder. Only then the idea of rolling can come in. So a cylinder can have a rolling action. It can also have a spinning action. So you can have both of these things.
What if you exert force on a point?
We can always exert a force on a point, but the question is that the direction of the force that you are exerting, is it exactly working along the center of gravity or not? If the force exactly works on the center of gravity, problems would be less. But if the force is somewhat offset from the center of gravity, you're going to have a lot of force. So that's exactly the way how the spin of the footballs are set.
Okay, sir. Thank you.
বুঝে গেছে?
Yes, sir.
Acha. So I'm actually covering a lot of ideas. I mean, I'm not directly
Yes, sir.
jumping into the solution of the paper because these are basic ideas that I need you to appreciate and comprehend. This makes understanding physics easier because if you have all the alphabets known to you, making sense of the word becomes easier. But if you, let's say, if you have learned only 10 or 12 alphabets and then you start reading English is gonna look really difficult for you and you're gonna lose interest altogether. So in many of your class 9 classes in the starting class, I'll be discussing a lot of additional ideas which does not essentially adhere to your syllabus or curriculum, but it is important that you understand this idea so that you get to have a directed way to process information. That's important. In my opinion, that's really, really important. Any questions so far?
No, sir.
No, sir.
No, sir.
Okay. একটু ওয়েট করো, আমি একটু পানি খাবো। So that was another thing that I really wanted to talk about. And so yeah, the defined logic that I was talking about is that so for the sake of simplicity, we are considering an object can be considered to be a single point, and those kind of assumptions can work in a lot of physics cases, which we're gonna see. Even in some cases, you'll see that they are making some huge geometric blunder. Yeah, for example, let me show you one of those examples of geometric blunder, which was very difficult for me to accept when I first came across to my theoretical parts, which I can explain it to you right now. There is a certain scenario. I'm just showing you these parts so that you get to know what you're gonna come across before you come across them. In one of the cases for simple harmonic motion or circular motion, whenever we try to কি ব্যাপারে delete হয় না কেন? আচ্ছা, এটা কোন একটা স্টুডেন্ট এখানে একটা অ্যানোটেশন দিচ্ছে। So I'm disabling participant annotation, but if you need that, ask me to or turn this on for us to have interactive communication. No big deal. So another difficult thing is that in the idea of a circular motion, let's say this is an object over here, and the object moves. The object is undergoing this circular track. So this is the object. This is the direction of the motion, anti-clockwise. Let's say. So let's say in a time of amount of t, this object moves from here to here, and it produces an angle of theta with the center. So let's say these are the two radius that we have, and the angle produced at the center is theta. So let's say the velocity, linear velocity over here was v, and linear velocity over here is also v, but both of these velocities are tangent to the circle. The magnitude of both of these arrows are exactly equal, but they have different direction. And because velocity is a vector quantity, change of direction can bring us change of direction also can mean acceleration. আচ্ছা, এটা নিয়ে আমি ঝামেলা করতেছি না। প্রবলেম যেটা করে বা হয় পরে দিয়ে সেটা হচ্ছে, you can see over here that we have a triangle over here. Okay, but well, to be honest, this is actually an arc, so this is not going to be a triangle per se. But if I just take out this side and if I try to draw this slice of this rectangle of this circle as a vertical structure, just to make sense with you. So one of the approximation that goes by to derive the further formula for this discussion is that, let's say this is that slice, and let's say it has a bit of a curve over here, right? It has a bit of a curve over here.
Chord.
Yeah, this is the arc length, this part of the circle, part of the circle? Curve. বুঝছো?
Yes, sir.
জি স্যার।
Asha. So let's say we have a bit of a curve over here. Now the discussion follows as the discussion goes forward is that this value is V, this value is also V, and this angle is theta. Okay. Now what they say after a while, considering this angle theta is extremely small or just small, we can assume this arc to be a straight line. First approximation. You see, it's not essentially, and it's very difficult to accept. Like, I can see it's a part of a circle. Why on earth would you define it to be a straight line? Because that logic was implied. Considering that theta is very small, if you consider that arc length is very small, would you be able to tell the difference whether this part is a straight line or a curve just by looking at it? You wouldn't. The difference,
Yes, sir.
the difference between a curve and the straight line would become extremely small provided this angle becomes too small. So I have drawn this angle to be a visible angle because I want to make sense of this figure. But if you consider this angle is, let's say, 1 degree or fraction of a degree, the arc length and the straight line drawn between these 2 points are going to be practically the same thing. So that's one approximation that they do. Then comes the second approximation, which is even weird, which is they are going to consider, they're going to consider these 2 angles, both of them to be 90 degree. Now, can you accept that in your geometric sense?
No, sir.
As long as you define it to be a triangle, can you have both of these bottom angles, each of them to be 90 degree?
Never.
Highly unacceptable, right? Because we know that the sum of these 3 angles are supposed to be 180 degree. But here comes the logic. We say that this theta is extremely small. Yes?
Sir.
Yes, one by one. অর্ঘ বলো। সুমাই তোমার কোশ্চেন একটু পড়ে নিচ্ছি, অর্ঘ বলো। হ্যালো, আচ্ছা, হ্যাঁ সুমাইয়া বলো।
স্যার আমি কোনো কোশ্চেন করিনি।
আচ্ছা, ইউ আর
স্যার এই দুটো লাইন কি ট্যানজেন্ট হিসেবে নিচ্ছে?
না, বলতেছি
স্ট্রেট লাইন।
বলতেছি these 2 lines are considered to make 90 degree with the base depending upon the idea that theta is extremely small. So if I just name this angle, let's say this is our center point O, and let's say this was starting point A, and let's say this point is B. So let's say if I draw this angle, let's say OAB. So what you do understand that angle O plus angle A plus angle B, the sum of these 3 angles are supposed to be how much? 180 degree, right?
Yes.
Okay. And you can essentially see that because these two sides are exactly equal, so angle A and angle B are exactly equal as well. That's good. That goes without saying. Now the logic that has implied that if theta is too small means, let's say this angle that is made as over here, which was labeled as theta, let's say I'm going to write theta over here. If theta is too small, let's say this theta is approximately 0. In that case, sum of A plus B becomes 180 degree, right? Or I can say angle A is
Approximately
approximately
180
degree. That's the logic that they imply over here. Now, this is a super high level of approximation, but it works. That's the beauty, or that's the ugly part, however you perceive it. For some people, it's going to be a beautiful thing. For some people, it's going to be an ugly thing, but that's the way it is. That, what I'm trying to mean is that by using appropriate logic, we can practically bend the rules of geometry, which is not supposed to happen, but we can for applicable scenarios. That if this theta is becoming too small, that is nearly 0, negligible. I mean, it exists, but it is as if it doesn't exist anymore. So it's too small. So practically speaking, angle A and angle B, each of them can be 90 degree. Now, can you deny this logic?
No, sir.
No, sir, it cannot be denied.
The problem
No,
is
No.
this logic is undeniable. At the same time, you are not very comfortable with it either, are you?
স্যার একটু এই সার্কেলের এটা একটু বুঝাবেন, আপনি যে এই সার্কেলটা এঁকেছেন, এই যে থিটা গ্রেটার দেন,
এটা
না থিটা গ্রেটার দেন,
acha, greater than na. So they forget about this part. I wrote a wrong symbol for the angle. I might as well get rid of this as a. Okay. So theta plus angle A plus angle B. So these are 3 different angles of this triangle. So by logic, the sum of these 3 angles are supposed to be 180 degree. This is supposed to be an 8. Doesn't look like an, it looks like a beam.
জি স্যার
So this is an 8. So the sum of these two angles are supposed to be 180 degree. And from this isosceles triangle, we can see it very well that A and B are equal. ঠিক আছে?
জি স্যার
So if
আইসোসেলেস হলে তো ইকুয়াল হবে
হ্যাঁ, because both of these are radius of this circle. এই যে এইটা radius, so OA is one radius, OB is also another radius. Because they are both radius, so these two angles are supposed to be equal. So the point that I'm writing over here, that theta plus angle A plus angle B equals 180 degree, makes sense. So if theta is too small, like extremely small, like negligibly small, so let's say theta is approximately equal to 0. So I give the approximation sign looks like this, curved equals to. So if theta is approximately 0 degree, it means that theta is very close to 0 degree, but it is not exactly 0 degree. It has some value, but that is too small. So if that is the case, in that case, I can say that the sum of this triangle is nearly 180 degree. In that scenario, one of these angle, A or B, can be approximately 90 degrees. So that's why I use the approximation sign over here as well. So we can practically, for the sake of our requirement, define these two angles to be 90 degree. But this is not supposed to happen. You cannot define both of the angles of two angles of a single straight line, of a triangle to be 90 degree. That is highly unacceptable. But provided theta is too small, we can logically derive this thing, and we can use it for our benefit. That's what I'm trying to get to in your head, that in cases of physics approaches, there will be apparently illogical steps, which is going to be helpful for you to process the problem afterwards. বুঝাইতে পারছি?
Yes, sir.
Yes, sir.
কোশ্চেনটা কে করছিল আমি খেয়াল করি নাই, আবদিন না অন্য কেউ?
জি স্যার আমি
বুঝা গেছে কি বলছি এখন?
জি স্যার
আচ্ছা, so these are the type of things what I mean by approximation. So এখানে একটা জিনিস হচ্ছে যে যদি আমাদের কোনো একটা সার্টেন কোশ্চেনে যদি স্পেসিফিকলি কোনো একটা সার্টেন ভ্যারিয়েবল কে নেগলিজিবল বলে দেয়, বা কোনো একটা সার্টেন ভ্যারিয়েবল কে বলে দেয় যে এটা আমরা আপাতত হিসাবে ঢুকাবো না, we can altogether disregard that. কিরকম disregard that? আমি সিম্পল কিছু এক্সাম্পল তোমাদেরকে বলি যে, ফর এক্সাম্পল, like I said, that for all of your motion parameters, air resistance is considered to be a negligible force. One of the key problems for air resistance, since I'm talking about air resistance, I might as well go the long way. Let me tell you give you a simple idea for how air resistance works. If we can find some animation, that would be very nice. Okay, I think that's it. আচ্ছা, এখানে সব অনেক হাইলাইট জিনিসপত্র দিয়ে ভরা। আচ্ছা, never mind. Did I search video option or did I search image options? আচ্ছা,
ইমেজ
no wonder. আচ্ছা, আমি একেই দেখাই, সমস্যা নাই। আচ্ছা, এগুলো আমার আর লাগতেছে না। আচ্ছা, আমার জাস্ট এই গ্রাফটা লাগবে, ওই জন্য এই গ্রাফটা কি লাগবে আমার? আচ্ছা, না, দরকার হলে এই গ্রাফটা আবার ইম্পোর্ট করে আনবো। বাদ। Air resistance দেখা যাচ্ছিলাম, so I was trying to show you air resistance. One of the important bit for air resistance can be described to be something like this. Let's say you have an object. Let's say for the sake of simplicity, let's consider a rectangular object. So I'm drawing it to be trapezium because I'm trying to show a three-dimensional object. Let's say this object is moving through atmosphere in this direction. So in front of this thing, we have a lot of air atmospheric particles available. So these are all molecules of air resistance, dust particles, and moisture and everything. We have some coronavirus presence as well. So I might as well show them with purple or pink. So there's some coronavirus present, why not? So let's say this is the atmosphere, and just to make good use of the atmosphere, because we have the opportunity, let's say we make that atmosphere copy paste. So let's say I copy this, and bam, more atmosphere, and bam, more atmosphere. Okay. So that was meant to be, actually never mind. So let's say now we're trying to move this rectangular plane across this atmosphere in the forward direction. So we're going to try to do this. If this plane is supposed to move forward in this direction, it will have to hit with these air particles and move them away out of its path to make its own way through. So if you consider the scenario, let's say here let's say as this thing comes forward, let's say after let's say this object is currently here and going through the atmosphere like that. So it's passing across the atmosphere like that. Now, essentially, if we, for the sake of simplicity, let's assume that one of the atmospheric particles, let me draw that with red just to be able to distinguish. Let's say this is one of those atmospheric particles, which is a molecule. So this molecule is going to hit onto this thing. The mass of this air molecule might be extremely small. For example, nitrogen molecule, carbon dioxide molecule, or oxygen molecule, which are the prominent things available in the atmosphere. But to make the metallic surface, which doesn't have holes, to pass through this atmosphere, it will hit onto this molecule. And by Newton's third law, I haven't taught you Newton's third law yet, but we will go through that. Just believe my words. By Newton's third law, to make this air particle move, the block will exert a force onto the air particle. So let me show you that force with red. I have a reason to draw it with black. So the force that will be exerted onto the air particle is gonna come from the block, from this metal plate, and by Newton's third law, this air particle is also gonna apply an equal amount of force onto this metal plate on the opposite direction. So the reason I have given these two different colors, I need to understand. I want you to understand that the black force is produced by the metal piece onto the air particle, but the red force is produced by the air particle onto the metal piece. So this force is experienced by which object? This red force is being experienced
by
by which
the
object?
block.
By the block?
Pillar at the block, whatever it is.
By
Okay,
the object.
by the object.
The object,
So
yeah.
by the object.
Object.
So object, block, plate, whatever you tell it. It's okay. I'm actually mixing up my words in my discussion anyway, so it's not a big deal. So as this metal block moves forward,
By the object.
each air particle or each air molecule is gonna hit this metal object, and that will exert some backward force. The magnitude of this force might, for a single air molecule, might be extremely small. But you need to understand that air is not made up of only one molecule. There are billions and billions and billions and billions and billions of molecules. Did you see the Trump video of billions and billions and? Anyone?
No, sir.
Okay. This might be a good time to give you some idea. I really want to take a bit of a break because I've been talking 1 hour non-stop. So we might as well see 5 minutes of billions. Have a look and entertain yourselves.
Funny.
It's golden.
Irritating.
Golden.
Annoying.
It becomes even better when I speed it up. Just have a look what happens when I speed it up. Acha, I might as well move the chat window. Let's say I'm gonna play at double the speed. So that was something. Anyway, so let's get back to the idea. So atmosphere is made up of billions and billions and billions of air molecules. So whenever this object is gonna go through this atmosphere, it's gonna collide with billions of particles. And each of those small particles are gonna exert a small force individually onto this object. But the cumulative effect, the additive effect of all of those collisions is gonna add up, to make a resultant force in the backward direction. So the velocity is working forward, the air resistance is always going to work in the opposite direction of the velocity. And that thing is very important for you to understand. Now, this air resistance is dependent on multiple variables. This is not a single variable dependent thing. One of the variable that affects the air resistance is how many particles do you collide with every second. Now think about it. If the object is moving slowly, every single second, within a single amount of time, so let's say every single second is just for the sake of discussion. If the object is moving slowly, it will collide with fewer particles. If the object is moving fast, it is going to collide with bigger number of particles. So that's one fact, that faster moving object would collide with bigger number of particles. Do you agree? Or in other
Can you
words,
repeat?
yeah, in other words, let me give you some idea. Let's say if this object is moving through the atmosphere at, let's say, 2 meters per second, then it is possible that it's going to cut across air particles. It's going to collide with air particles, which are within a 2 meter length of cuboid space. So it looks a bit odd, but that's what I'm trying to show you. So let's say this much length over here is 2 meters. So the object is going to cut across this much space. But if the object was moving at, let's say, 10 meters per second, then how many particles should it collide in the same amount of time? Then the length of this cuboid space is going to be 5 times as big. Am I correct? Try to understand. So I might as well copy this and make it 5 times longer. So within the same amount of 1 second of time, this object is gonna, I should make 2 more. Okay, fine. Let me just make
So the force will be more.
the force will be more. That's the point that I'm trying to make. If the object moves at 2 meters per second, the number of air particles is gonna collide is gonna be 1/5 compared to the amount of particles is gonna collide if it's moving at 10 meters per second. Because within 10 meters per second, it's gonna cover 10 meter distance in the atmosphere. So the number of collisions for 10 meters per second is gonna be 5 times as big compared to the number of particles collision for an object moving at 2 meters per second. Can you appreciate that idea?
Yes, sir.
Yes, sir.
Do you understand why did I draw this figure? To show you an idea that how much space or volumetric space that the object is going to collide with as it passes across the atmosphere. So that's important for us. So the faster an object moves, it essentially collides with a bigger number of particles. That's factor one. The factor number two is that whenever you collide with something with a bigger amount of speed, you will essentially experience a bigger amount of force as well. Think about it. If you throw a ball onto the wall at a lower speed, it's going to bounce off not very strongly. But if you throw a ball at a very high speed, it's going to bounce off really strong. So when the object is moving faster, it is also colliding with the individual air particles with a much bigger speed, which means if the speed of the object is high, this forward force will also be large, and this backward force from each individual air molecule will also become larger. So higher speed of the object is attributing to two factors. First of all, it is increasing the number of collisions per second. Secondly, it is also increasing the individual amount of force available from each collision. So both of these two things will add up to a much bigger increase of this air resistance. Can you appreciate this fact?
Yes.
Sir, can you repeat what you just said? I didn't understand.
I'll help. When the object is going to move from a low speed compared to a high speed situation. So if the object moves at 2 meters per second, and if you compare for the object to be moving at 10 meters per second, compared to the low speed situation in the high speed situation, first of all, it will be colliding with bigger number of particles per second. So number of collisions will be more. And secondly, it will collide with each of the air particles, experiencing a bigger individual force from each collision. So each collision will give you more force, and the number of collisions per second will also become large. So together, they will essentially add up to a much bigger air resistance. See if this idea is understandable.
Sir, doesn't Newton's third law state that the forces will be equal?
Yeah, the forces will be equal and opposite, but those two forces are not experienced by the same object. Object is pushing the air particles forward, air particles are pushing the object backward. So because these two forces are working on two different bodies, you cannot sum these up, or the resultant force cannot be zero. I think you are going in that direction, right?
Yes, sir.
Yeah, we can only assume, or we can only apply the idea of resultant forces for two different objects whenever for resultant force for multiple forces whenever all these forces work on a single body. But that is not the case for air resistance, because the two forces which come from the third law, they will essentially work on two different bodies. One exerts a force on the second one exerts a force on the first one. So you cannot add these up. Addition of two forces is only applicable when both the forces work on a single body.
But is it possible?
That's what I'm trying to tell you. You should be able to take your decision. I'm not telling you the answer. I'm trying to give you tools to decide for yourself. You can only do resultant of multiple forces if the forces work on a single body. These two forces that I've drawn over here, are these two forces working on a single object?
Yes.
No.
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 Think about it.
No, sir.
No, no.
The block is
No.
pushing the air particle forward and the air particle is pushing the block backwards.
Different object.
So one force, this black force was experienced by the air particle and the red force was experienced by the block. So you cannot sum these up. That would be inherently wrong. The idea of resultant is only applicable for cases when multiple forces work on a single body, not on different bodies. So did I answer your question?
Yeah.
So you cannot apply the resultant force concept over here because the forces are not working on the same object. Come to think of it. Getting back to my original discussion is that whenever the object is moving forward, we are having an increase of air resistance by at least two factors. One of them is that there will be bigger number of collisions per second, and each collision individually will exert a bigger amount of air resistance. So together you will have a much bigger amount of air resistance. You see, because air resistance is dependent on these two variables, the calculation of air resistance can become extremely difficult because the value of air resistance will not be a fixed amount of force. What I mean is something like this. Let's say we have a cuboid object which looks like this. Should I get rid of these parts? আচ্ছা থাকুক, সমস্যা নেই, it's not a big deal. কি আঁকতেছিলাম যেন, কি যেন আঁকতেছিলাম?
Keyboard, sir.
Yeah, I was trying to draw a cuboid. Yes. Drawing a cuboid in Microsoft Paint might be a nightmare, but I can try. Cuboid কেমন আঁকতে চাইলো? ও আচ্ছা, হ্যাঁ 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 আচ্ছা, কিউবয়েড না, আমি নরমাল অবজেক্ট দিয়ে দেখাই। মনে করো এটা হচ্ছে একটা সার্টেন সারফেস. লেটস সে দ্যাট সারফেস ইজ not smooth. Let's say this surface is rough. Onto this surface, let's say we have placed an object. Let me just label this object at a different color so that we can distinguish the object. So let's say brown. So if I say that this surface is not smooth and there is a friction force between the contact surfaces of the object and the surfaces, let's say that friction force. So let's say friction, I usually represent friction force by this force due to resistance or resistive force. Let's say that force is defined to be 10 Newton. Now, typically, this 10 Newton force that exists between these two planes is a fixed number. So what I mean is, if you apply a force of, let's say, 2 Newton on this object, the friction force is also going to be 2 Newton. It's not going to be more, and the object will not move. If you apply a force of 8 Newton onto this object, this friction force is also going to be 8 Newton, and the object is not going to move. If you apply a force of, let's say, 50 Newton on the object, then the friction is going to be limited to its terminal value, because the maximum friction value was mentioned to be how much? 10 Newton. In that case, this frictional force will reach its maximum value, which is going to be 10 Newton. And now you have to understand that currently this 10 Newton is also working on the object, and this 15 Newton is also working on the object, because both of the forces are working on this object. We can sum these up. So in this case, the resultant force is going to be how much? This is the symbol for resultant, which is with the summation sign. This is going to be
5 Newton.
15 minus 10, 5 Newton. In which direction?
In not direction.
No, not
Right. Right direction.
Exactly. So we're going to have a resultant of, let me just show that resultant with the beautiful arrow, because I can. So let's say the resultant force over here is going to be 5 Newton. So the object is going to move forward in 5 Newton forces. So that 5 Newton will be our driving force. So you see,
The friction is more.
the friction cannot be more, because I initially said that the maximum friction between the two objects was 10 Newton.
No,
But
if we exert a force of 5 Newtons, and
yes, well,
if we exert a force of 5 Newtons and the friction tends to be more than 5?
No, that's not going to happen. That's what I'm trying to transfer in your head. Think of a regular scenario. Let's say you have a heavy object placed on a table. If you push it by a small amount of force, you'll get the exactly equal amount of force back as long as you don't reach to the highest value of the frictional force. Friction will always try to oppose the motion, which means it will try to make objects come to rest, or it will try to objects to become stationary. So the frictional force will never be a driving force on an object. So if you apply a 5 Newton force on this object, where the maximum friction force can be 10 Newton, your friction force is also going to be matched with that value. Or in general terms, if I say, try to understand this next sentence carefully. If your applied force is something smaller than the 10 Newton, the friction force will be exactly that. But if your applied force is something bigger than 10 Newton, your friction force will be this much, and the remaining force will be able to move this object. That's how friction between two surfaces work, which usually has a fixed value. So it is possible to work with this number because this is not a velocity dependent factor. Speed যত বাড়বে আমাদের এই ভ্যালুটা কিন্তু বাড়বে না। মনে করো তুমি 5 নিউটন ফোর্স দিয়ে তাকে অ্যাক্সিলারেট করতেছো, the object starts from rest and it goes on forward and the speed slowly increases. This 10 Newton force would remain to be 10 Newton force. So it's not going to be a variable. But that is not the case for air resistance. As the object moves forward with higher velocity or higher speed, the faster it moves, the bigger is going to be air resistance. So air resistance is going to be a continuously variable force. Do you see the trouble here? Incorporating a continuously variable force in an equation is extremely difficult. I mean, it's not impossible, but that level of competency is not introduced at your level. That's why throughout our discussion of our motion or moving objects up to our A2 level, we're going to consider air resistance to be negligible. For mathematical conclusion, for mathematical questions, we are always going to consider it negligible. But for theoretical questions means for decision-making explain questions, suggest and explain, describe and explain, state and explain. For explanation question or word-based questions, air resistance effects might be asked. So it is important that you understand the fact properly, but you also at the same time appreciate the information that we would never have to deal with this air resistance force in our mathematical proceedings, but we have to have a good understanding of what the air resistance is all about, provided that we can work with this one. Do I make sense?
Yes, sir.
বললাম বুঝা আছে কি বলতেছি?
Yes, sir.
Yeah.
So conceptually,
Yes, sir.
soundly বুঝতে হবে. Conceptually, you have to be able to grasp it properly, but you will never have to do any mathematical calculations regarding this factor. So that's another way to put this whole idea. So this is the part that I wanted to tell you, that in your questions, if a question, whether if you are ever working with a mathematical question, whether the question states it or not, in almost all cases, I shouldn't say almost, in all cases of your CIE syllabus, all the way up to A2 level, for mathematical questions, we will always consider air resistance negligible. But for theoretical questions or explanation questions, we might be asked that considering air resistance, what difference could we see? So that's also an important thing. Yeah, for example, if I give you a basic idea, you guys have come across the idea of the parachutist graph. I think in your schools you might have come across this
Terminal
graph.
velocity.
Yeah, terminal velocity and everything. So this is the graph that I'm talking about. I'm going to discuss this graph in detail. I'm just trying to take a reference. Do you remember this graph?
Yes, sir.
That the parachutist starts to fall from their parachute from this point. He falls at almost uniform acceleration. Blah blah blah. A lot of things happens over here. One of the important part that you need to understand that the entire idea of this whole graph is based upon the idea of air resistance. If you consider resistance to be negligible, this person should always fall to the ground with an ever increasing linear velocity and eventually gets splashed as it hits the ground. This person is never going to have a terminal velocity. The entire idea of terminal velocity is applicable because air resistance is there. Think about it. If air resistance did not exist, if we consider air resistance to be negligible for the case of a parachutist, would he ever be able to decelerate?
No, sir.
It wouldn't happen.
No.
Because
No,
air
sir.
resistance,
Impossible.
impossible, exactly. Because air resistance does exist and it is available to us. The object or the parachutist can actually eventually come to decelerate and come to rest, and all these variations are possible because air resistance is a force that we have available. So you have to be able to logically use this idea to properly explain parts of these graphs or different segments of these graphs, or why certain thing is happening in certain ways. So you have to be able to answer theoretical questions, logical questions, but you never have to work with some value of average distance that will be incorporated in your question. খুব রেয়ার কেসে যেটা হতে পারে, মানে it's highly unlikely but it's not impossible, let me just tell you that if they ever give you a mathematical information where your array resistance have to be included, they will never give you it to be a variable. In rare cases, like extremely rare cases, they might tell you that the object is moving over here and the array resistance is a fixed value of, let's say, 10 Newton. If they ever want to incorporate array resistance in your questions, they will always mention it to have a fixed value. Fixed value forces are workable. We can make equations and go ahead with them and everything, but variable forces are very difficult to work with. So বুঝা গেছে কিনা? Any questions so far, kids? No, I think okay. If you have question, raise your hand or write the question over here, so I will take reference from that. So আরেকটা জিনিস যেটা বলতেছিলাম সেটা হচ্ছে আদিন একটা কোশ্চেন, আদিন asked me a question that how would that those graphs can be operated. So let me just take a simple velocity time graph from there. Acha, or I can actually draw this thing. That might be actually less time consuming other than looking it up in the internet. So let's say I'm gonna draw a VT graph over here to my best capability of scale. Let's say this is our time axis, and here we have second, and here we have velocity. Let's say this is given in meters per second. Okay, so let's say I give you some values: 5, 10, 15, 20, 25. So okay. Now let's say we have a certain speed time graph that looks like this. For an object, we have given us, we are provided with a speed time graph. I'm gonna give some dots first so that I don't mess it up altogether. So let's say 0 to here, to here. Okay. Beautiful. So let's assume this is a given VT graph. So I want you to appreciate the coordinates of these points. For the object starts from 0, 0 points. I didn't actually label 0. I must. So the object starts from at t equals to 0 at 0 speed. So it starts from 0, 0 point. It goes up from here to here. So it accelerates over the first 10 seconds, reaches to a maximum velocity of, final velocity of 20 meters per second. Then it goes, maintains that speed for the next 10 seconds. So it's a horizontal line, no acceleration. Then it accelerates once again from 20 to 25, going from 20 seconds to 25 seconds. Within this 5 seconds of time, it goes from 20 meters per second to 40 meters per second. And then from there, it eventually comes down to rest at the 30-second mark. So let's say we are provided with this equation. So we want to calculate how much is the total distance covered by this object in all of this information. So there are multiple different ways we can do this thing. I personally like the trapezium a lot because trapeziums are, in my opinion, easy to work with. Not essentially very simple to visualize, but trapeziums allow you to do less calculation, less writing. So let's say I'm going to use this figure, but I might be using triangle rules and everything. So I'm going to just keep a fresh copy of this figure over here. Let it be there. This is amazing. I mean, I can just copy paste figures like that, but it is never possible in a whiteboard, on a physical board, that is. So this is nice. So I'm gonna try and divide this whole graph into convenient shapes of trapezium. So have a look what I'm gonna do. So let's say I'm gonna draw one trapezium by drawing an assumed vertical line over here, and then maybe over here. So I have divided this whole thing into 3 segments. Here we have a trapezium, here we have a trapezium, here we have a triangle. But we could go for more, but I'm gonna show you this one first. Now, what I need you to understand that for this trapezium, these two are the horizontal lines, sorry, parallel lines. The parallel lines are the horizontal segments. But for this trapezium, the vertical lines are the parallel segments. Do you see them? Now, এই জিনিসটা আমি কেন হাইলাইট করতেছি, এই জিনিসটা বুঝাই। আমাদের ট্রাপেজিয়ামের বেসিক এরিয়া ক্যালকুলেট করার ফর্মুলা ছিল হাফ ইন্টু a প্লাস b ইন্টু h, ঠিক না? তোমরা তো এই ফর্মুলাটা সবাই চিনো। Half into a plus b into h. Now, the way we usually define this thing, that a and b are the what? Parallel lines or the horizontal lines? How have you learned this? How do you define A and B? Yes.
Are the parallel lines.
Parallel lines.
A and B are the parallel lines, and h is the perpendicular distance between those two lines. So if I go ahead and use this equation, I'm going to do the calculation over here because niche space time. So if I go for the area of this one, how much should this be? This should be half of the sum of the parallel lines. So here this parallel line has a length of 20, and the top one has a length of how much? How long is this line?
10.
This has a
10.
and this vertical space is how much? That this distance
20.
20.
from this axis, that is exactly is also 20. That's for our first trapezium. এটা একটা গেল। Second trapezium জন্য কি আসবে? For the second trapezium, these two are the parallel sides. So
T and 40.
is 20,
20, 40.
and then one is 40. 20 plus 40, and the perpendicular distance is 5.
5.
5.
And then for the last part, that is the triangle, if you go for that part, how much can we write? Half into base into height. So you can triangle formula. Base হচ্ছে 5
into 40.
into 40.
To 40.
এটা পুরোটা ক্যালকুলেট করে দেখো যে কত আসে। Get me a number. Everyone use your calculator and get me a number. মামুন এসকেলের বিলটা কি বাইরে না ভিতরে? আসে নাই? বেলা ডুবে গেছে, এটা তো ডাইকে আনা দরকার। আবার পরে দেখা যাবে যে আশা ভাই দোকান বন্ধ করে চলে গেলে আবার লক খাই যাবে। কত আসে দেখো তো?
$550.
550.
Okay. 2 of your classmates said
550.
3 of you. Okay. Everyone দেখো যে মিলে কিনা 550 আসে কিনা।
Yes, sir.
ঠিক আছে? So এটা হচ্ছে মনে করো একটা procedure. I personally like this one because in that case you have to work with fewer segments, so you have to do less calculation. However, if this feels uncomfortable for you, you can also divide this into multiple triangle and rectangles. So সেটা আমি করে দেখাচ্ছি। If I try to do this calculation using triangles and rectangles, I can also divide this into multiple places like that. Let me use
Divide the
now. So
trapezium.
other than using the trapezium, if you don't want to use the idea of trapezium, you can. It's just going to be a bit more time consuming, but you should be comfortable with what you're comfortable with. Okay. So have a look. Now I have divided the entire thing into triangles and rectangles. That's it. So triangle 1, triangle 2, triangle 3, rectangle 1, rectangle 2. So এখান থেকে যদি আমি ক্যালকুলেট করি তাও আমি সবগুলো ভ্যালু বাই করতে পারবো, বাট ইম্পর্টেন্ট পার্টটা হচ্ছে ইন্ডিভিজুয়াল লেন্থস গুলাকে যাতে আমরা মেস আপ না করি। That's important. So if I go for this calculation, so I'm gonna just try and do this because I'm trying to show you my logic over here. It's not essential that you have to learn this, but for some people this might make better sense. For some people the trapezium rule might make better sense. So whatever that your brain is more used to or your brain can capture easily, adopt that method. No big deal. There's no hard and fast rule that you have to use trapezium rule to be able to solve this problem. Trapezium rule can save you some time. That's the benefit that you have. But it's not compulsory. যে trapezium rule দিয়ে করতে হবে বা triangle rule দিয়ে করতে হবে না. It's not compulsory. So if I go for this one, how much should we have over here? Half into base into height. Half into 10 into 10, 10 into 20. Then for the rectangle, how big is this rectangle?
10.
Okay.
10 into 2.
This exercise 10, this exercise 20. So that's a 10 into 20. And then this rectangle, on the vertical side, we have 20. That is over here.
5 into 20.
And over here, 5. This is 5 into 20. And then this triangle, this is the important bit. Have a look. For this triangle, the vertical side is from 20 to 40. So this side is how much? This side it has a length of
10.
10.
10.
No. And you need
20.
to visualize. This is the line over here, and this peak is labeled at 40. So
20.
this much is 20.
10.
And
20.
this much is 5. Well, this figure is not essentially very perfect because I hand drew it. So this is supposed to be half into 5 into 20. And then if we go for the last triangle, which is the same as earlier, which should be half into 5 into 40. So এখন এই সবগুলো ভ্যালু আলাদা আলাদা করে ক্যালকুলেট করে দেখো কত আসে. If your calculation is not wrong and if our writing is not wrong, I should get the same answer 550. করে দেখো কত আসে.
Yes, sir. 550. 550 আসে, sir.
550 আসে।
সবাই একটু ক্যালকুলেটর বসায় দেখো just to convince your own selves.
Yes, it's 550.
অর্ঘ তোমার কথা শুনতেছি না বাবা.
জি স্যার।
আচ্ছা ঠিক আছে. So the reason I showed you these two methods is to convince you how to do that. So এটা একটা প্রসেস আর আরেকটা প্রসেস যেটা সেটা হচ্ছে যে দাঁড়াও তোমাকে আমি ইন্টিগ্রেশনের বেসিক আইডিয়াটা আরো ভালো করে দেখাইতে পারতাম. Do you kids know how the area of circle becomes pi r square? I mean, did you kids ever come across any geometric proof for this one?
No, we did not did such formula deduction or
It's not included in a syllabus, so it's not a harm that you don't. But did you ever see this?
Yes.
Yes, sir.
Yes.
মানে হচ্ছে ওই যে ছোট ছোট ট্রায়াঙ্গেল ভাগ করে তারপর সেগুলোকে উল্টো
Yes,
করে
sir.
বসায় and the whole length becoming 2 pi r. Do you get what I'm saying?
Yes, sir.
Did all of you come across this visual? Actually, many of you might have not. So I would like to show you this part because this is an important bit for my next part of that explanation, and it's never a harm if you just come across some. This one. Have a look at it.
Pi r squared gives you the area of a circle.
Small video.
But where does pi r squared come from? First, we'll draw a circle and fill in its area. Next, we will divide it into large equal parts and arrange them in a rectangular formation. As you can see, it barely resembles a rectangle. So next, we will divide the circle into small equal pieces, and we will arrange them in the same manner. You can see that it appears more like a rectangle. So if we divide the circle into even more smaller pieces, you can see that every time the shape becomes more like a rectangle. So how small must we divide a circle before we can get a perfect rectangle? Well, we can keep on dividing the circle into small, smaller, or the smallest pieces you can make. But the answer is to divide the circle infinitely many times until we cannot distinguish the lines, and eventually the circle can now become a perfect rectangle.
Infinitely small pieces.
So, the area of the circle is equal to the area of the rectangle, which is equal to base times height. The height of the rectangle, as you can see, is the same as the radius. So height is equal to radius. To find the base, we need to look at the circumference of the circle. And when we compare the base and the circumference, we can see that the base is equal to 1/2 the circumference. Remember that the circumference is equal to 2 pi r. When we combine it with 1/2, the 2's cancel out, and base is equal to pi r. So now base times height becomes pi r times r. Combine the r's together and we have pi r squared, which is equal to the area of the rectangle, which is equal to the area of the circle. So pi r squared can be used to calculate the area of any size circle that exists.
কিছু বুঝলা?
জি স্যার বুঝে গেছে।
It was very simple, right? But when they break things up like this much, things become very easy to visualize, right?
Yes, sir.
I really
Yes,
like
sir.
these kind of animations a lot. So many of you might need this, or many of you might have come across this a bit earlier, and many of you might ask, I might be asking yourself this question: this is not a math class. Why is he doing geometry 2 with us? I'm doing this because I like to do this. That's the simple explanation, and it helps. It helps, even if it helps one of the kids in the class. I'm willing to take this effort all the way. So. Based upon that idea, if you remember that in that video, this person actually divided that circle into infinitely many pieces to make it into a perfect rectangle. That's the whole idea that I'm trying to talk about. So if I just try to go ahead and try to show you the formation for a curve, to calculate the area under a curve, this is the logic that I'm trying to talk about. So let's see, this is a axis system that we are provided, and let's say we have a bit of a curve. So I'm going to draw a curve over here. So functional curve. So if you want to measure the area of this under this curve, let's say if I draw a straight line from here to here. So let's say we want to find out the area under this curve. So I want to calculate this green area. So I might as well fill this in green area. So if I want to calculate these up all together, one of the ways that we can do is divide this entire curve segment into very small trapeziums. Now, the reason I'm telling you very small trapeziums is because whenever you take really small trapeziums, okay, I might as well choose black for this one. Yes. Whenever we choose very small trapeziums, the smaller the trapeziums are, the closer this side can represent a straight line. So let's say I'm now dividing them into different trapeziums. I'm not essentially bothering to make them equal in width, but with equal width, the calculation becomes easier, but we don't have to make it equal width. The point that I'm trying to make is that now, even, I mean, if you have a good look, if you look at zoomed in look for this curve, I mean, this segment is not essentially a straight line. But if you make a lot of circles, for example, let's say a circle, if you take a lot of segments, let's say this one, and I'm gonna copy this transparent selection. Yes. And let's say if we make this into a really big number, or so let's say if we divide this circle into too many small pieces, that will essentially give us a pretty much a most approximate trapezium over here. And by adding up the area of all of this individual trapezium, we can effectively calculate the area of this whole curve, area under the whole curve. So that's the basic idea of dividing the trapezium. The bigger number of trapezium that you use, more accurate your value will be. If you wonder why more accurate our value will be, there is a geometric explanation for that as well. So I might as well show you that part so that I can make sense with it. That is, if I just if I just do not take too many pieces, let's say if I only consider this whole thing as a single triangle, if I consider this whole thing as a single triangle, which is going to be wrong, obviously, then the side, then this corner of this triangle might as well look like this. So this is going to be the side of the triangle. So you see, if you consider this to be a triangle, you're making some mistake. What kind of mistake? You are calculating this much area more. How much area? This much area. Because area under the curve is actually this green part. But if you consider this entire curve as a straight line and try to calculate the area of this under this straight, assume this whole thing as a triangle, you're calculating this much area more. So which is a wrong procedure. We can essentially reduce that error. By doing one single thing. That is, let me copy this up.
Can't we subtract the red portion?
If you can
Like the
calculate,
arc.
if you can calculate that part, it would be nice. But how can we calculate the area of this red red portion? I mean, if we don't know the area of this part because this is a curved situation, so you don't have a geometric formula to go ahead and calculate the area of this thing by some equation. That's the problem that we have.
Yes, sir.
আমি আবার বলতেছি, we don't have a geometric equation like triangular area formula হচ্ছে half into base into height. You have a fixed geometric equation, you go for it and you pretty much get the number. But we don't have a definitive equation to calculate the area of this segment or calculate the area of this segment. That's why we are going through all of this trouble. So this is the amount of error that we are gonna make. But if we don't do that, let's say if I don't do that and only draw one, if I divide this whole thing into two triangles, let's say if I just draw one more triangle, so one vertical line to divide this into two segments, then I can actually get rid of a huge amount of error just because I'm gonna have two segments will give us a smaller error. Smaller error. Let's say in this case, I'm gonna consider this part as a single straight line and that part as another straight line. So if I take that part, so let's say over here, I can draw one straight line, assuming that this curve is a straight line, and I can draw another thing considering this part as a trapezium. So now the amount of additional area that I'm calculating for the area of this green part is the green part added with these two slices. We should be doing this red. So this is the amount of error that we are making. So have a look. Whenever we consider the whole thing as a single stage, we made a bigger amount of error. Whenever we have divided this into two spaces, then we have made a smaller amount of error. Do you see that? Can you appreciate this information?
Yes, sir. Sir.
Yes, sir.
এতটুকু একটা বড় একটা এরিয়া আমরা কি করতে পারলাম, হিসাব থেকে আমরা স্মার্টলি বাদ দিয়ে দিতে পারলাম। Just a second, আমি কোশ্চেন নিচ্ছি, একটু ওয়েট করো। Other than doing this, if we made it into, let's say, 4 segments, let's say if we made it into 4 segments, I would like to use black for this one. In that case, our error would be even smaller, because if I make it into 4 segments, then I'd be considering, I need to zoom in a little bit, I'd be considering this much line, oops, I would be considering this much line to be a straight line and this much line to be a straight line.
Sir.
Yes.
Sir, তার মানে তো স্যার কোনোদিন পারফেক্ট হবে না।
কোনোদিনই পারফেক্ট হবে না, but like I said, told you at the very beginning that there is a question of making something zero and considering something negligible. Remember that part?
Yes, sir.
So এখানে আমরা so that's the point that I'm trying to get at. That was the whole point of talking about all of those idea of zero and negligible in the very beginning. That is going to imply our calculation over here. So if I go for 4 segments, now I can get rid of these segments of error. So I can essentially make these parts white. So I'm not making these errors anymore. I'm only making these small slices of errors. The more, yes.
Can we make small trapeziums and do it instead of doing this?
Yeah, that's exactly what I'm trying to get at. That's the point that I'm trying to show you, that the bigger number of trapezium you're going to divide this whole segment into, the small this error is going to become. যখন তুমি একটা সিঙ্গেল স্টেজ দিয়ে করছো তখন তোমার অনেক বড় একটা এরর হয়েছে, যখন তুমি দুটো স্টেজ দিয়ে করছো তখন এরর আর একটু কমে আসছে। When you are going for 4 stages, then your error is even less. If you go for 10 stages, you will be doing even less error. If you go for 100 stages, you'll do even less error. If you go for infinite divisions, you'll do 0 error. And infinite divisions are practically করা possible না, hypothetically করা possible, but practically তো তুমি can you make infinite divisions over here? That's not going to be pragmatic. So the idea is that we should convert this into convenient number of segments that is easier for us to calculate, where these lines can be considered to be straight lines. So the idea is that whenever we have divided this into significant number of good number of divisions, let's say 10 divisions or something like that, in that case we can say that all the errors that we are making by considering all of these curves as straight lines, that amount of error is negligible compared to the value that we are calculating. So we did make some error. That's true. This is not exactly correct. That's also true. But whatever the amount of error, we are minimizing it by choosing bigger number of segments. Do I make my point?
Yes, sir.
Yes, sir.
We are doing some error, but we are defining the amount of error to be negligible compared to the amount that we are working with.
Instead of trapezium, we can also calculate it by using rectangles and triangles.
We totally can. I mean, you can essentially draw a rectangle over here, and those rectangles would be perfect, but this triangle will be still giving you the error. That's also perfectly good. বুঝতে পারছি কিনা?
Yes, sir.
জি স্যার।
একদম শুরুতে আমি যে ফিগারটা দিছিলাম ওখানে যে প্রবলেমটা ছিল যে that
Yes,
figure
sir.
was totally working with rectangles. I didn't want to show you this
Sir,
rectangles.
আপনি
That's why I got rid of that figure, and now I'm showing you the exact way that how trapeziums can actually help us to calculate the area under the curves. হ্যাঁ বলো, আদিন বলো।
স্যার এই ডায়াগ্রামটা আবার একটু বুঝাতে পারবেন? এই দুইটা আমি আমি এটাইতে একটু গোলমাল হয়ে গেছে।
কোশ্চেন বলো, কোথায় বুঝো না বলো, I'll help you.
এই দুইটা ডায়াগ্রামের ডিফারেন্সটা।
On the first diagram, we assumed this entire curve as a single straight line and calculated the entire area under the curve, assuming it as a straight line. So the triangle was the area. So we made an error of this red amount. In the second step over here, we tried to divide it into 2 triangles. So this was the error amount. This was the error amount. So we could get rid of this. Sorry, this was the error amount. Na? This was the error amount. So we could get rid of this triangle whenever we consider this into two triangles. So this was a straight line, and this was the other straight line. When we divided it into 4 triangles, we could reduce that error amount into these small slices. So the bigger number of divisions we are making, we are making a smaller and smaller amount of error. That's the significance of these 2 diagrams. বুঝে গেছে?
Yes, sir.
আদিন বুঝছো? Hello?
I had a question.
Yes, go ahead.
Sir, what if we 1/4 of a circle, square, rectangle, whatever it is, like what if we find out the area of the square, then subtract the 1/4 of a circle from it?
So you're telling us that triangle রেখাকে এটুকু সাবট্রাক্ট করে দেওয়ার জন্য? Is that what you're proposing?
So my question was that what if we find out the square or rectangle, whatever it is at first, then subtract.
সজীব, তোমার কথা কেটে আসতেছে। অর্ঘ্য, তোমার চ্যানেলটা মিউট করো because you are not passing information, so please mute your channel. অর্ঘ্য, we appreciate that. সজীব, তোমার কোশ্চেনটা এখানে লেখো, পাবলিক চ্যাটে লেখো, everyone লেখো. Your voice was breaking up, so Orgo, I cannot hear you right. Your voice is breaking up. Write the question. If you have any question, write the question. Will the equation ever be given for using integration? For your physics syllabus, no. As far as my experience goes, for your CIE syllabus all the way up to A2 syllabus, you would not be asked to do an integration. For all the cases, you will have to go for area calculation by this kind of segmentation. And the smaller number of segmentation that you're gonna go for, the more accurate result you're gonna get to the actual value. For your CIE physics syllabus, you will never have to do integration. The formula for integration will never be provided, or no. Shojib and Arko, I'm waiting for you to write up your question. So please make it happen and fast. Acha. By the time, next class. Next is by the time I come across these two questions, I'm not sure if they are actually writing up these questions or not. I would actually propose that we shift these classes, this Friday class, half an hour late. So 5:30 to 7:30. তোমাদের কারো কি ক্লাস কলাইড করে যদি 7:30 পর্যন্ত আমরা ক্লাসটা কন্টিনিউ করি? Anyone?
No, sir.
No, sir.
Because quite a good number of parents
sir.
and kids actually personally messaged me and they requested that this to be resolved. It would be very helpful for them if we shift the class half an hour, so that both of our timings are basically identical. I'm perfectly okay with it because I don't have any collision. My other class starts at 7:30. So okay, Shojib gave us this question. Before I get into the question, so it is decided from this point onwards, I'll be changing my routine schedule, and you can also make this change to your routine schedule. I'll be also posting this to our Facebook group as well, that Friday classes from henceforward are shifted half an hour late. So permanently it will be 5:30 to 7:30. ঠিক আছে? So for everyone. Let's agree on that. And Shojib, the question Shojib has placed: what if we find out the area of the square or rectangle, whatever it is, then subtract 1/4 of a circle from it? Okay, how do you know that this curve is essentially a circle? We don't know that. This is a curve. Every curve is not a circle. There is parabola, there is hyperbola, there is exponential equations, logarithmic equations. Those equations do give you a curve, but they are not circles essentially. So subtracting a circle can be based upon the idea that whatever the curve that we are working with is a part of a circle, but we don't know that for a fact. So that's why going for a subtraction is not essentially helpful, because it's not a definitive decision. So does it make sense? Could I answer your question?
Yes, sir.
Achha. Beautiful. So I would like to conclude our class today because it's almost Maghrib prayer time, and also I'd like to tell you one more thing, that from our next class we'll start the equations of motion, or the 4 equations that we have. That is the topic we're gonna pick up in our next class. So, and we'll also proceed with the definitions of the second chapter. If you get the next class কবে? নেক্সট ক্লাসটা রুটিনে যেদিন দেওয়া আছে, আমি নেক্সট ক্লাস প্রত্যেক ক্লাসে একবার করে বলবো না, রুটিনটা দেখবা, কষ্ট করে দেখে বোঝার চেষ্টা করো। না বুঝলে আমাকে আবার পার্সোনালি মেসেজ করে ডিরেক্ট করো, স্যার রুটিন বুঝতেছেন, আমি রুটিন বুঝাই দিব। But answering this question directly is not a very fruitful way. Thank you very much, kids, for your patience, and I hope it was an enjoyable class. If not, I'm sorry. All the best. Stay safe.
So can we leave?
Yeah, the class is over. Thank you very much.
Bye, sir.
Bye.
Bye, sir.